clear? Can you clear them up? That
You are breaking up,
you would
Jeremy.
have,
You're really in the matrix.
obviously have to turn the plane to stay on the longitude line, and if you don't turn the plane, you'll veer off the longitude line.
Is that to me, Jeremy? Is that to me? You're breaking up pretty bad. I don't know if you're still there or not.
Well, he's not breaking up. He's lagging. We get all the words, but they just take forever.
Yeah. Well, Bacon, that graph is really super interesting. I'm glad that Gio posted it so I can actually drag it over to my desk and look at it some more. I'm thinking there maybe is a factor of this rate of change of this tangential velocity is coming to play here. So maybe following the exact tangential path initially with the Earth rotation having such a low tangential velocity, maybe you take advantage of that directionally, and then later on you mitigate that by going more southward to be able to take advantage of the higher disparate tangential velocity from where you started. I'm not quite sure. Maybe where you're at, John, as well, is kind of spinning around in my mind about what's really happening there.
That's kind of what I'm thinking. Yeah, that I think you're thinking weird, the same thing.
But intuitively, I'm thinking, no, head directly to it, at least as Jeremy's talking about it, and along the way, we apply that turning force, but staying on that longitudinal path. That's kind of where I started. And now I'm questioning myself, like I think you are as well, based on what Bacon has just posted. So
yeah, and you see how if you do just fly down that longitude line, you are in effect pointing to where that airport's going to end up without even thinking about it.
Not to mention,
hold on, Zanick. Can you guys hear me?
Yeah.
Yes.
Yeah. Can you just clarify for John, because he's under the misconception that if you get in your plane and you just fly straight and you don't turn and you don't put any turning force, that you'll just follow a line of longitude. Can you just tell him that's not true and correct him, please?
I think he doesn't think that's true either. I think he knows.
Yeah, that's not true.
I mentioned that earlier.
So John, back to my scenario. We're both at the North Pole. You're not going to apply any turning forces to your plane. You're not going to turn. You're going to aim at where the airport's going to be. You're not going to follow a line of longitude, but you're not going to turn your plane or apply any turning forces at all. We clear?
Right. I think that if we can really neglect any winds, any other effect, that I think I won't quite follow a line of longitude. I just think it'll be very close.
Okay. Thank you. Okay. That's the path you're going to take. I am going to take a path where I'm always flying at the airport, and I have to turn a little bit throughout the course of the flight to stay on that, so that I don't miss the airport. Otherwise, I'll miss the airport if I don't turn.
Okay, well, now I'm a little confused. Just to be clear, I thought you were, so I'm saying I'm going to fly down a line of longitude. That's what I'm going to do. And to do that, if I do that, but John, then I think that a little better. Okay. Yeah.
John, hold on. You're flying at where the airport's going to be. You're not going to turn. That does not keep you on a line of longitude.
Right. I think I agree with that, but almost.
Okay.
It's not a very big difference.
Okay, it's not a big difference yet. I am going to fly where I'm always flying at the airport, and I'm turning a little bit, or I'm having to apply turning forces or bank or scatter, crabbing, whatever you want to call it. I have to apply some kind of force to make the plane turn. Who takes the shorter path, John? The guy who turns or the guy who doesn't turn?
Right. So I think the guy who follows the line of longitude, which you can only do by applying some forces to stay on that path, I think that ends up being a slightly longer path. I think that's my current thinking.
John. Yes, we are on the same page, John. Yes.
So Bacon
showed you is very misleading. He should have used the North Pole. It would have been super clear for you to use the North Pole and the equator.
I mean,
I don't know. I'm not sure I understand Bacon's thing, but at least he understands the point.
Of course you don't,
because
it's very convoluted and very misleading. It could have been much easier if it was North Pole to the equator.
What if we equated
merry-go-round, bro? Would have been way easier, dude.
Well, I want to argue that with John still. Possible.
What if we equated to the crosswind? What if we started out knowing we had a no crosswind type of force going down south of the North Pole, but we knew we were going to go into 100 to 200 mile jet streams down farther south? Wouldn't it make sense to kind of take advantage of that by angling initially when there's no crosswind into the area where there is crosswinds to take advantage of the crosswind?
Yeah,
That was actually,
well, absolutely. Are you talking to me,
offer-
Zanick? Sorry.
I think I'm just thinking out loud when we start equating things, and it's a good analogy to be equating this deviation to crosswinds equaling Coriolis. Coriolis is it's a lot smaller, but it's still the same type of force acting.
I mean, I think that's really the key thing to remember in all of this is the Coriolis force is so small that it just disappears in the noise of a flight. But not to say that it isn't there. I'm interested in the theoretical thing. I think it technically makes a small difference, probably an unobservable difference, but I think it does make a small difference. Obviously, flights take advantage of the winds. They fly in order to take advantage of tailwinds, etc.
I think what we did was. Well, yeah, we were quick, but I think we did equate that to be a 1.5 mile per hour change per hour. 1.5 miles per minute per hour of acceleration. It's like really, really tiny along as far as acceleration goes along its way.
Yeah, I get 0.03 feet per second squared, which is 1,000 times smaller than gravity.
Right.
Okay. Can I jump in? I want to offer a scenario here. Let's say we got two big buttons. One turns off the atmosphere. The other one turns off Earth's rotation. Right? Let's hope no precedent because we're all dead. But in this scenario, there's just an airplane. And let's start at the North Pole. So I don't offer a convoluted scenario. So we have an airplane in the North Pole, and we can both turn on the rotation of the Earth, and we can turn off the atmosphere. Right? So let's think about a scenario where the Earth is spinning, but there's no atmosphere. So we have like a magical plane that doesn't use the atmosphere, just hovers, right? Of course, in that scenario, you want to aim where the airport is going to be, right? Because that's simply the easiest way to get there. As soon as you take off, if you take off in the direction it's going to be, there's no atmosphere, there's nothing there's no influence in your path. It's just a straight path in the inertial frame till you get to the airport. Does everybody agree with that? At least on the globe side? Or did that make sense?
Yes, I agree with that.
Okay. Right. Now let's turn off the rotation and turn on the atmosphere.
Meaning rotating winds or not rotating winds?
A stationary Earth. Earth that doesn't
stationary
spin.
Earth. Station. Okay.
So now we just fly straight a great circle route because we're flying through air and Earth isn't spinning, so we don't have to worry about any Coriolis. We just go straight to where we see the airplane, and that's the best path. Okay. Now if we turn on both, if you turn on only the rotation, then and not the atmosphere, then we're back to the first scenario. But if you do turn both the rotation and the atmosphere, none of those two scenarios is the optimal path anymore. So the one without the atmosphere is no longer the optimal path because now you're interacting with the atmosphere that is rotating with the Earth. If you try to follow the optimal path, okay, that's the thing that I'm trying to point out, that you shouldn't agree with Jeremy, because what he seems to be suggesting is the best path is where the airport is going to be, which is not once you have an atmosphere. But also a great circle route is also no longer the optimal path. There's something in between, which is much closer to the great circle route. So if you follow great circle route, that's going to do it.
So let me just ask you, Bacon. You agree, I think, don't you, that if the plane was constantly traveling through an atmosphere that was perfectly stationary with respect to the rotating Earth, right? So no winds. If that was the case, then, and you wanted to follow the plotted great circle route, I think you would have to constantly bank a little bit to counter the Coriolis force.
Exactly. So that's what I'm saying. The path that would take the most advantage of Coriolis is not the great circle route, but it's almost the great circle route.
I agree with that. I'm sure that's true. Yeah, I'm completely sure that's true.
What I'm also saying is that it's very different than just aiming at where the airplane is going to be. I'm saying that the path that aims at where the airport is going to be is just vastly different and definitely not the path you want to go. Because as I showed on the animation, you have to simply travel much faster because you're taking a curved path.
Well, I still have to think about this more, but I certainly do agree. There's no question in my mind that the difference is small because the Coriolis effect is so small. There's no way that a plane actually takes into account the Coriolis effect except automatically, right? There's no computer calculating it and telling the plane what to do. The plane is just following the Great Circle route. That may not be the most efficient, but the extra efficiency you could get by doing whatever correction you have to do is so minimal that it's just not done.
I'm gonna say that the amount of fuel you would save by following the optimal path that accounts for Coriolis is probably more expensive given the computational power that it takes for your airplane to compute it.
Well, I doubt that, frankly. So, but it does make it. There might be other reasons to object to it, just in terms of simplicity of understanding. Yeah,
I have objections. Yes, please. One, you don't need a supercomputer to do the computing. Snipers do this on the fly, so you're not going to need any crazy supercomputer to do this. I could probably do it with a cell phone. Okay. And
wait.
the little amount you would be off would be 30 miles. Zanick did the math for me on this before. If you fly from Alaska to Hawaii and you don't turn, you'll be off 30 miles. That's 30 less miles you got to travel. Now, that may not be a lot on one flight, and it may only be a half a mile or an eighth of a mile on other flights. However, there's a story of an airline who took an olive out of every first class salad and they ended up saving 50 G's a year. So little bits add up to lots of bits when you're dealing with, big corporations.
Now that 30 miles that you're off could be a kind of a perpendicular distance, which doesn't translate to 30 miles difference in the path. I don't know what that calculation was. I mean,
however
like
many
for instance,
miles it is.
Yeah, if I end up
however many miles it is, it'd end up being a lot over the course of time.
Well, yeah, I don't know.
I don't think
one olive. John,
I don't think that's
olive.
obvious.
Yeah,
I
think
one olive, John.
miles. It's more about I think it's more like 400 or 500 miles, and I don't remember that calculation. But I think people have talked about trips that are 4 or 5 hours long, going north or south, being if they were ballistics, they'd be off 400 or 500 miles, not 30 miles. That doesn't make any sense.
Well, I don't see how that could be.
You gave me the wrong math in the past. I'm not surprised. However, you would save some mileage, and those mileages would add up over the course of time. You'd fly shorter paths if you were flying shorter paths. John, did you get my example from the North Pole to the equator?
Yeah, I did. But my point there was just that, what I'm going to do is I'm going to travel down a line of longitude rather than along that putative shortest path. Now, one of the problems with that, of course, is that the winds themselves. Well, I'll just leave it there. The point is that if I just travel down the line of longitude, I'm traveling on essentially the path that automatically puts the airport where it ends up. It's not quite the same. But it's because, deciding to fly down that line of longitude means that I am rotating with the Earth as my destination moves, and I end up there. Maybe with a slightly longer path. I don't know. I still have to think about that. But it's just
John,
it's not a very big. It's not the difference between aiming and going to where the city is now. If I do that, then I won't be traveling down a line of longitude.
Yes, and you won't be turning the plane at all either. And we agreed that if you don't turn, that is the shortest path you could possibly do is not turning, right?
Well, I still think there's a little bit of either dishonesty or misunderstanding about turning and not turning. In order to travel along a straight line path, on the rotating Earth. Okay, fair enough. I'll just say fair enough. I do think that the point is that it's not always the case that applying a turning force causes the object to turn. There are lots of situations in which that's not true.
In the case of winds, yes, but we're talking about the Coriolis effect, and in that case, it is true.
Fair enough. That may be right.
So if if I
Bacon's.
had to fly, if I had to fly from the North Pole to the equator, obviously I would want to figure out where the airport was going to be, so I don't have to turn or apply any turning forces at all. That'd be the shortest path. We're going to say hypothetically, there's no winds.
Well, I don't know if Bacon's simulation is involving any turning. I think it is, because the way I'm looking at it, just intuitively, and John could, kind of back me up on this as well. He's taking off eastward because we have a lot of tangential velocity that we want to tangential momentum we want to retain, and we go eastward actually of our target until it gets up to the north area where the tangential velocities are very, very low. Then it starts going east, utilizing all that buildup of tangential velocity to kind of accelerate and go toward the target. But the difference between going straight line, like the guy on the surface is going north on a train track, let's say, if they could all go the same airspeed, I guess, or net velocity, then they end up getting there at the exact same time almost, from what the simulation shows. And I'm still trying to digest that. But I mean, you see what I'm saying with that, John? Is that something that's kind of, it's very interesting.
I think it is getting at one part of Bacon's simulation that I don't think I fully internalized, right? That radical curvature in the one path, I think, may not be quite what it appears to be if you think about it properly. And that's why I need to really do this on my own. I'm gonna try to repeat Bacon's stuff myself.
It looks like it stops